Our next topic of study is quasars. So we talked about blazars, radio galaxies, and active galaxies. So we realized that BL is certain objects, which we later became, realized are the cores of really active galaxies. We started calling blazars. So likewise, we're going to talk about a quasar. The term quasar actually came later. What happened was 1960 or so. Um, Sandage and Matthews discovered the optical source of a radio signal that goes all the way back to shortly after World War II in the third Cambridge catalog, object number 48. And so, object number 48, they found a radio source, but they couldn't find out where the radio sources were coming from. And so what happened was that this was right near the ecliptic, and so eventually the moon passed in front of here, and they noticed one object disappeared just disappeared from view, just as the radio sources stopped, and then reappeared just as the radio sources began as the moon was going by, and they identified that as this thing that just looked like a star. And so they decided to say, well, it looks like it's just a radio star. In fact, when I was a kid, science fiction author, was also a science author, Isaac Asimov, wrote a book about astronomy, and one chapter was on radio stars. And that's what they were calling these things at the time, a radio star. The only thing is, when you discover a star, the first thing you do is you do spectral analysis of it. In this case, the spectral analysis didn't help any, because normally you see spectral lines that you recognize, and that helps you figure out whether there's an O, B, A, F, G, K, M star, or what have you. This is before they had L, T, and Y. But here we had something that didn't seem to match. And so the spectrum didn't tell them anything. And so it looked like a star. They realized that it got brighter and dimmer, kind of like a variable star. So it acted like a variable star, but they couldn't find the spectrum of it. And after a while, they started finding other quasi-stellar objects, and that was the term QSO, quasi-stellar object, because it was like a star, but it wasn't. So eventually, they found one 3C273. Identified it, and it actually had a jet of stuff coming out of it. And then a lot of the radio signals coming out of the jet. And so that was suggestive that you have accretion going on. But again, the best telescope they had did not indicate anything other than just that it was a star. The spectrum made no sense at all. We're used to what spectrum looked like. First of all, it was a emission spectrum. Normally, with stars or galaxies, you get an absorption spectrum. So down at the bottom, we have a galaxy absorption spectrum. And so here we had an emission spectrum. So that didn't seem to match anything that we knew. Stars and galaxies have absorption spectrum. 1964, physicist Chu is writing an article about these quasi-stellar objects in the periodical called Physics Today. And so he decided that quasi-stellar object, writing it over and over again, was kind of hard. So he came up with the term quasar to describe these things. Well, eventually, though, they realized with 3C273, somebody recognized the spacing of the spectral lines was the same as the spacing of hydrogen spectral lines. They were just all in the wrong spot. That what should have been a red hydrogen alpha line was way over in the infrared. And some spectral lines that should have been in the ultraviolet were in the visual. And so that's why no one recognized the spectrum, because the spectral lines were all in the wrong spot. That meant this thing was supremely redshifted. In fact, I say supremely redshifted. It's really hard to actually measure the spectrum, because it was very hard. It was so dim to measure. So what I had before was a very idealized thing. What you have here is actually the spectrum of 3C273. You just barely see these spectral lines, and they're entirely in the wrong spot from what anybody expected. and they were like massively redshifted. And so Martin Schmidt made these determinations, and then all of a sudden we realized that we're looking at something super redshifted. So what does super redshifted mean? Well, Schmidt insisted that meant that they were super far away. Again, remember the relationship, the Hubble relationship, that the bigger the velocity, the bigger the distance. And so redshift times the speed of light is the velocity. And so that would give a huge velocity and thus a huge distance right there. Okay. Redshift is change in the wavelength of the wavelength. As they started realizing what they were, they found more and more quasars. They did not all give off radio waves. In fact, 90% of them don't give off appreciable radio waves. However, all of them are extremely high redshifts. And so what are the redshift? What are these quasars? Why are they so redshifted? And so why are they so very redshifted? One thing they used to think was maybe they're objects being spit out of our galaxy. In fact, in the 1960s, when the first Star Trek, gotta have a Star Trek reference, the first Star Trek series that came out, they still thought some of these quasars might be things kicked out of our galaxy, and so the Starship Enterprise was investigating a quasar-like object at one point. Turns out that's not really what's happening. So they're not really objects, within our galaxy. They're not being expelled from our galaxy. Maybe there's something in our galaxy that's super high gravity, because that can give us high redshift. Well, that's been ruled out too. So that they must be something really far away. But if they're that far away, to be visible, they have to be super bright. Okay. And really, they were arguing continuously about what these things were until the 1980s. And that's when they finally decided that they really are objects that are super far away. Okay, so some of them had redshifts that are, 0.5, some of them redshifts 0.8, some of them redshifts. A lot of them had redshifts of, 2, 3, or 4. Well, wait a minute. How can you have a redshift bigger than 1? Because if the velocity is redshift times the speed of light, something bigger than 1 would mean a velocity bigger than the speed of light. So does that mean they're actually going faster than light? No, of course not. They can't go faster than light. So what does that mean? It means that life is more complicated. And that's where special relativity comes in. Remember, special relativity, time is stretched or altered when you go really fast. So that changes the distance as well. So relative velocities had to be taken into effect. And so really, z is not just the speed divided by speed of light. So z is, it used to be just speed divided by speed of light. Now z is a much more complicated relationship here, which means we do algebra on that to find velocity. Velocity is not just z times c, it is that equation that has z in it times c. And so that just makes life a little more complicated. But it does allow us to solve here and find out that as we go and look at the velocity, that we get farther and farther away, redshift gets bigger and bigger and bigger, and this is not really linear. And so your book has kind of a graphic in there that gives z and gives the velocity as a fraction of the speed of light. And so that's how we now find these distances. So what are these things? They had all these arguments about what these things were because they were super, super far away. And so there were suggestions. Maybe they're like blobs of matter and antimatter running in together. They couldn't explain why the universe had so little antimatter, so maybe that's what this was. Maybe there were white holes, the counterparts to all the black holes that are near us. People had all kind of really wild ideas. And then finally, by the 1990s, they were starting to see hints of galaxies surrounding the quasars, meaning the quasar is really the core of a galaxy. a super bright core. So once again, super bright means Eddington limit, super mass. So they found more and more quasars that had galaxies surrounding them. So that means that the quasars are now going to be active galactic nuclei. So quasars are still in this realm of active galactic nuclei. And with that, we start to realize that quasars, blazars, radio galaxies, and Seyfert galaxies are all different aspects of the same kind of thing, a supermassive black hole that's accreting things.